Okay, we're going to look at sinusoidal functions and how to transform them. Specifically, we're going to first we're going to review the parent functions in case this hasn't been made clear to you yet along the way in the things you've practiced with sine and cosine, just as basic functions, what kind of anchor points to focus on and some of their features. And then I want to move into horizontal transformations. So that would be period adjustments where the length of the sine wave or the cosine wave is either increased or shortened. We call that a horizontal shrink or stretch. And we could do that by adjusting the period of the function. So we'll look at that, and we'll also pay attention to, I might make this a second video, but we got to talk about phase shift. So how to take the whole wave and move it either left or right, and how that's most easily dealt with, hopefully. All right, so parent functions, sine and cosine here. This has probably come up in some of the things you've watched and practiced already, but sine, really we only have to trace or check 5 anchor points, and they're what we call the quadrantal angle values. Let me get my blue pen working here. So sine of 0 is 0, sine at 80 degrees, or pi halves. We're going to usually deal with radians, so pi half radians. If you can remember that pi is exactly the same, pi radians is exactly the same angle measurement as 180 degrees, then it makes pi halves radians easy to remember as 90 degrees. Okay, so just a quick recap on the anchor points for sine. So the thing about sine, you know, when we refer to the sine same shape, but they start in different spots. So you can tell you're dealing with a sine curve if it's going through the midline of the graph and heading upward from there. Okay, so these 5 anchor points, the first one, the most important one, being at the origin, and then the next anchor points at the local max, back to the midline, local minimum, and then back to the midline heading up again. So that's one full period. Okay, so one period of sine function is equal to 2 pi radians. Okay, so the length of that cycle. All right, now in contrast, or similarly, cosine, like I said, same shape and very similar anchor points, but instead of starting out at the midline, cosine wave has its first anchor point right at the top of its amplitude or the local max. From there, the predictable shape continues. So you go through the midline, you bottom out halfway through the cycle, back through the midline, and then back to a local maximum. So these 5 anchor points are sufficient when graphing. Oh man, this tablet gets hard to use towards the bottom here. So, okay, I will get used to this eventually, or at least finding the undo button quicker. Okay, so put little arrows on the end here because these do continue in a wave, same shape, pattern forevermore. But again, you could see that our period here, length of one cycle, one period, is exactly 2 pi radians. It's just we had a different starting anchor point. Okay, so a lot in common. I want to move over here to this side of the page now and talk about, I just called it the model. And the truth is, Khan Academy and a lot of textbooks kind of present it this way, but I have a problem with the way they show it on the inside here. There are easier ways to deal with this, and the workaround is not that bad. So for starters, I'm going to write out the model that I prefer to use. It's got easier handles, if you know what I mean. I'll explain that in a second here. A, okay, they have A. That's your amplitude. That's your outside layer multiplier. That's either going to be a vertical stretch or shrink. On these anchor points for these parent functions here, you can see the A value is just a phantom 1. So that's why the amplitude here, the distance from the midline, is 1. That's what A does. Okay, and then sine, and this is where I differentiate a little bit. I like to write it out as a factored form, okay? So in order to factor b out of the bx plus c, if you're going from a Khan Academy problem, for example, or a textbook problem, a different resource than what my notes are going to be here, you're going to have to factor that b out of this term here. So you would see like a b over c kind of a thing. And I'll show how to use that here in a sec. Okay, so you can get from here, I don't know why I did a capital B there for some random reason. All right, you can get from the model that you see in Khan Academy to what I think, good grief, that D looks like an A. Sorry. By factoring that B out of this internal expression here, factoring B out of BX is not that difficult, but factoring whatever this B value happens to be out of some wackadoodle fraction or number, essentially, I wrote it upside down. Gosh, if I undo button anymore here, I am going to have to. So this should be C over B. Oofda. Okay, and I know that's true because if I multiply this back through, I get B times X is BX, and B times C over B, well, the B value, whatever that is, would cancel with the B value in the bottom, and you'd just be left with C again once you expand that. Here's why this is great. If you could see what's being added or subtracted on the inside layer here, you could tell how far your phase shift is, either left or right. If you're adding a value here, you're shifting left. If you're subtracting, you've got a phase shift right. Okay, so in my notes, like when I'm teaching this to a set of students in person, and I get to kind of run the show live like we always used to do it, I write it out this way. Okay, and this might be something you run into in pre-calc and hang on to if it works for you. And again, I'm using sine here, but you could have cosine going. They both have the same period and kind of features going on. Now, I'm not going to go to the trouble of writing C over B in this model. If we were in person in the classroom, and I guess I can say it now too, but you've got your amplitude, you've got your B value, which here's the thing about B, and we'll talk more about this in the example I do here in a minute. But B is not the period, it helps you find the period. So if you have 2 pi divided by the B value, good grief, B value, then you can figure out what the period is. So if B is 6, you're going to have 2 pi over 6, which is pi thirds. You've got a period length of pi thirds instead of 2 pi. So B is crucial in finding that amount. And then here you've got a phase shift. Phase shift C. And because it's subtraction, you would just say right. So if C was 10, for example, X minus 10, you would say phase shift 10 right. Okay. All right. And then D is your midline or your vertical shift. I like to refer to that as the midline because these functions are so visually centered or balanced across that midline. Okay. All right. I'm going to go to a different page now, but that's a quick review. And I think I'll actually cut the video here before I start the next example. But that's a good review on the anchor points for sine of x as a parent function, cosine of x, a lot of similarities, but different starting points. And you might be getting used to radians still. So that's something too. But yes, we're going to be dealing with the model in Khan Academy a lot like this. And we could find that phase shift by dividing that constant by the B value so that we could see separately what are we adding or subtracting to that input layer variable. And if we're adding there, that's a phase shift left. If we're subtracting a number, phase shift right. Okay, I will see you in the next video in just a minute.